Good morning, afternoon, evening, wherever you are, whenever you are. My name is Bruno Turkley, and this is a talk that I prepared for Tech Ready. What is this talk going to be about? Well, let's get into that. It's going to be about building a Java-based RESTful service that runs in a Docker Linux container within the Azure Container Service, specifically as a DCOS cluster, within a DCOS cluster. So again, my name is Bruno Turkley. I am a cloud engineer essentially at Microsoft. I'm on this team called Executive Escalations. My job is to kind of work with strategically important partners and companies, bring them up on into Azure, understanding their business model, their current technical architecture, and moving them forward in adopting Azure. Now, much of my work does relate to containers, as that is today one of the more important technologies out there. So we're going to cover all that in the next few slides. So there's some pretty ambitious takeaways here for this session. First of all, let's just all agree that containers are at a tipping point. They're at the point where I believe they're going to really get mass adoption in production at the enterprise. Part of that journey means more than just the containers themselves. We'll actually define that in a moment, but we're also talking about orchestration here. What does that mean to orchestrate a container? And who are the big three orchestrators out there? What are they doing? How do they work? We'll take a deep dive there. Also, we'll take a look through examples here on how to containerize an application. From there, we'll start looking at the Azure Container Service and what that means and how you provision it. Finally, we'll also look at how to deploy containers into this cluster, and then what role does Devops play in terms of deploying my application automatically without any human involvement, and put it out into staging and then ultimately production. So the takeaways, really one of the core takeaways here is how you would run a really large clustered application in Azure, and that's what really the reason we're containerizing a Java application to run in a container inside the Azure Container Service. And so we'll have very hands-on and concrete demonstrations here about how to take a Java application, compile it into a WAR file, place it into a container, and run it within a provisioned ACS cluster. There'll be much more to this than I'm just talking about here, but that's the high level. And then finally, one of the main reasons that containers are so popular today is that they really automate the application delivery pipeline, CI/CD. Continuous integration, continuous delivery. We'll look at some examples here of how I implemented that. Well, in terms of level set, let's just define very quickly what a container is, which is a complete file system that encompasses everything, including the code, the runtime, the systems, tools, libraries, anything that my application needs to run. So here in this diagram, you'll notice, for example, I have my code, right, that I've written. That code really represents my application, of course, but it's running within the context of a container. Inside that same container are all its dependencies, and those dependencies include the environment variables that application needs, the files, the libraries, the drivers. All those are basically shipped together as one unit inside of the container. Now that typically means, of course, that I can take this entire container here and deploy it as a single unit, meaning that the application travels with all of its dependencies. Therein lies all the powers and benefits. Why containers are becoming mainstream? I think the core reason they are is because they encapsulate the dependencies. That's what I just basically talked about previously. Now, when you have the encapsulation of dependencies, that increases your portability. Clearly, if your application has everything it needs, it means it can pretty much run everywhere. It can run with a great deal of portability. And as I'll explain more in future slides, it enables Devops, because now that container can go from the developer's computer to the test environment for QA, to a staging environment, to a build server. It can go across the entire delivery pipeline in a predictable way. Application density. This essentially means now that when I deploy to a virtual machine, I can take my container, deploy it to some environment. Well, that environment does not have to be pre-configured. It can be generic. That means I can deploy almost any type of container application into that VM. It doesn't need to be pre-set up. And that allows me to pack in more running containers, more applications running on a single VM. So that's one core reason for app density. The other reason is essentially at a higher level that these containers are very small, very efficient in terms of the amount of memory and disk space they occupy. And also you'll notice a lot of conversations today around microservices. Can you do microservices without containers? The answer is yes, but containers make microservices easier. It's easier to upgrade and update a microservice using containers, and essentially you can think about the encapsulation of dependencies making microservices easier to support and build out. Let's walk through a quick example here about how some of these things work. So notice, for example, here that I have old school virtualization here, plain old VMs. What that means is that if I have one application over here and one over here, they're both talking to version 1.7 of Java, of the Java runtime. That's all fine and good. Everything works as needed. But let's imagine that I then upgrade my version of Java to 1.8. Well, that's fine for application 1 over here, but guess what happens when I get to application 2? It could potentially not be prepared to deal with that upgrade and therefore may not operate quickly or efficiently or may even not run at all. Now contrast that with the world of containers, the other form of virtualization here. So again, now we're running a containerized workload. Notice that my application 1 comes with version 1.7. And sure enough, container number 2 over here running my second application comes with it, its dependencies, which is 1.8. So in a sense, you have portability here, you have better support for upgrades and for that app to kind of move around without breaking things. It also kind of harkens back to the previous slide about application density. So the bottom line here in this slide here is that I can continue to add applications to this VM without breaking other applications because each application brings in its own dependencies, in this case, the Java runtime version. So we finished talking about the portability component. Let's now talk a little bit about the DevOps. Now DevOps is all about taking your code, once the developer checks it into GitHub or whatever repository you have, and then automatically triggering a build process where that application gets tested and placed into a staging or production environment, all without human intervention. Now I've got a bunch of like bullet points here to the right that describe why that is such a good thing. In general, successful software companies utilize DevOps to optimize the way they deliver their apps. It leads to a lot of efficiencies here, from recovering faster from failure, fixing security challenges, and just spending less time doing unplanned work. You can read about this. Puppet Chef have this white paper here you can see in the lower right corner that you can go read about, but there's a lot of evidence to support that companies successful at DevOps have many benefits that they enjoy. Now there's a lot going on this slide, but let's not get intimidated by all this. Let's once again describe some of the reasons why app density can be high here. Notice, for example, here that in the traditional world without containers, okay, that's the left side of this diagram, we have a couple build servers that are, say, hypothetically the way Microsoft builds out Excel, how it compiles Excel. Imagine, if you will, that the VM that does the compiling of the Excel source code also maintains all its dependent libraries. So you have multiple VMs, each one of them having to include the Excel dependent libraries in order to compile Excel source code. Same thing would hold true for a Word compile process, whereby we need the Word dependent libraries on every VM that's going to combine the VM source code. Now contrast once again with the world of containers, whereby we have a generic build server, a generic VM that simply puts into the containers the dependent libraries along with the source code. So once again, the containers have both the libraries needed for compilation as well as the source code of Word. So in other words, over here on one generic VM, right, we have both a Excel build process taking place as well as Word, meaning we can mix and match build processes on a single generic VM. We don't need to pre-equip that VM to support only that compile process for either Word or Excel. In other words, a generic VM can do everything. And that allows us greater build density, allows us to actually not have to worry about configuring all the correct VMs before building out Word. And it's probably the way the developer had built out Word as well, how he had compiled it. In the case of Excel, it's probably a bunch of build servers. It's kind of an overly simplified scenario here, but I think you get the picture here that in the world of containers, it makes the build pipeline a lot easier to manage because you can leverage generic VMs. So it probably means that because of this greater density, and I've heard reports from 4 to 8 times more running applications on a single VM than in the traditional non-container virtualized world. So 4 custom VMs versus 2 generic VMs. Quite a big advantage in the world of containerization. So one of the big deals here when you think about containerization is this notice of this motion towards microservices. Now, we're moving away from the traditional monolithic 3-tier architectures. They kind of make a lot of friction. They're not easily extensible or scalable. They're fragile. Developer IDEs are getting kind of too big and slow. So this move to microservice architecture is the big new kind of step forward here. And what that simply means is that we have these autonomous single responsibility services that do one thing real well, kind of like the Unix philosophy. It's a fundamental shift here. And so each microservice owns its own state, and that's why here you could see we have each of these different modules, whether that's trip management or notification, having its own state. Think about perhaps the way Uber could hypothetically be architecting its applications. They would break down the various components into these microservices, each one with its own data store. Now, whether or not you have a REST API here as basically the communication points, that's kind of up to debate. Some people feel that the synchronous nature of REST, the whole request response architecture, doesn't lend itself. You want more of an asynchronous model with message passing and streaming. So at any rate, this is a microservice architecture. Everything is independent, meaning that you can test, deploy, and scale independently. Gives you a lot more flexibility that way. And again, you'd communicate traditionally asynchronously through message passing. Imagine that you have 4 VM hosts and you're running containers across all of these VM hosts. As you can see, this can get to be a little complicated. Like, how do you know where each of these containers are running? How would you address it from different other containers? And each of these containers could be running different types of applications. So this problem gets exponentially worse as you grow the number of containers, the number of nodes or VM hosts in your cluster. So we need to be careful that things get complicated very quickly here. So the answer becomes here that you need some type of orchestrator needed to manage this set of running containers. It helps you simplify deployment and manage these containers across a very large pool of virtual machines. And you have 3 dominant cluster orchestrators today that are supported by the Azure Container Service. Docker Swarm, Mesosphere DCOS, which is really not Mesosphere, it's an open source DCOS kind of cluster operating system for the cloud, and Kubernetes. So at any rate, these are 3 open source kind of packages supported by the Azure Container Service. And the beauty about all this is the Azure Container Service gives you a choice between these 3 orchestrators. Now the decision to choose one over the other, fairly complex kind of process to analyze the strengths and weaknesses of each one of these. But let's just say that Microsoft provides choice at this level, that you're not forced to any one, you have an option. No vendor lock-in here. So today, in this demonstration, we're really going to be working with DCOS. That will be what we provision in the Azure Container Service. That will be what we deploy to once we take our container and need to deploy it into the cluster. So the question you might be asking, what exactly do these cluster orchestrators do? Well, number one, they help provision your container to run inside the cluster. You may be keeping your container in a repository or under a registry, for example, hub.docker.com, and the provisioning process could automatically download your container from the repository and put it into the cluster. So that's part of its process, to provision new virtual machines as well as deploy your app. So when we think about provisioning and deployment, it's kind of at two levels. Provisioning is about the VMs, but deployment is taking your app or container and putting it into the cluster. Health monitoring. So part of the job of an orchestrator is to make sure your container or your application is running correctly. And if not, take some remedial actions to spin up a new copy of your container. Scaling. Maybe there are some metrics you've set up such that, for example, if usage of a CPU exceeds a certain threshold, you want the VMs to automatically scale up. And the way the Azure Container Service is built out, it uses VM scale sets. So you can set up some kind of thresholds to kind of scale up and scale down. That differs upon orchestrator. Monitoring and logging, you want the orchestrator to help monitor all your apps. You want it to control logging such that you have a central place where you can see your logs. You wouldn't want to have to kind of connect up and determine what VM is running your container, what the logs look like. You want the cluster orchestrator to make that easy to use. Security, a good orchestrator will kind of lock down ports and make sure that there are no vulnerabilities, maybe help in adding security patches. Storage, there's also the notion of each container having its own data store. The question becomes, if the container gets rescheduled on another VM, how will the orchestrator help establish that the storage follows it or that can be supported by that container's new location? Networking, there's the notion of software overlays, IP addressing. Each one of the orchestrators implements its own version of networking. That's one of the tasks we want the orchestrator to do. We want it to make it easy to connect up and communicate with various nodes, various containers running in the cluster. And service discovery is kind of related to that in the fact that you have a bunch of containers running all over your cluster. What about being able to connect up to a specific instance, being able to address it, know where it's running? That's what service discovery is all about. And then finally, the registry, knowing how to download from a central location, whether that's a private or public repository. We'll be looking at hub.docker.com for such functionality. We talked about 3 of the top most popular ones, but let's remember there are others here. For example, Amazon has its Elastic Container Service. It's proprietary. Google has their own kind of container as a service offering called the GKE, the Google Kubernetes Engine. Red Hat has OpenShift. Docker has a non-open source version of their orchestrator, and so forth. So let's just be clear that there's no single dominant orchestrator today. There's a host of options that you can choose from. Okay, at this point we are going to engage in a series of demos. Much of what remains is very, very few slides and a bunch of hands-on demonstrations of how to do everything in great detail. So stay tuned and hold on tight. We're about to go down a demo journey here. So before getting into the web app itself, let's talk about the data that this app will expose. This means that the user from a browser is going to go try to hit this RESTful endpoint, and that RESTful endpoint will execute a Java application that will do a query against a MySQL database. So let's take a look at that database here. I'm going to basically log into MySQL, and we'll take a quick peek at the actual data that we wish to return from our application. So we've just pretty much typed in the MySQL with the username password. Let's go ahead and log in now and take a look at this database. So the database is called Azure Course, and the actual select query looks like this. We're going to select from a table called Courses. So again, what we're doing here is showing the data that we're going to expose. So notice over here, I've got record 0402. The course title is Mesos rather, and there's a variety of other rows here that we can select from, like there's some for Python and so on. So again, the reason I'm showing you this is the back-end database that we're going to query from using the Java RESTful service. Let's begin by looking at our Java app, which is essentially utilizing the Spring tool suite as the IDE. It's the model view controller architecture. Let's take a look at Azure Course in a moment, which is the model component, and Azure Course Controller is the controller. Now looking at the model component, Azure Course.java, there are essentially 3 data elements that are relevant here: course title, course number, and notes you can see here as private members of the Azure Course class. The Azure Course Controller, a simple class that has some objects to talk to the database, as you see here. The connection prepared statement and results set. We have a URL that the browser will connect up to. When doing so, it will connect up to this method, get Azure Course. It's a very simple method. It essentially takes in potential parameters here, but it will return a collection of Azure courses. So you see here below we have the list of Azure courses. That's a collection that will be populated in the following section here. We'll connect up to our MySQL database. We'll execute a select statement against it. We will then loop through that result set from that query and then return in JSON format to the browser that collection of courses. We also have Gradle as our build test environment here. The way that works, it compiles our application, performs some unit tests, and if successful, builds the WAR file. Now let's take a quick peek at that file here that does the unit tests. It essentially makes sure that upon the URL that we talked about, that Mesos is returned as the course title. You can see the browser window illustrating all of that. And essentially this means that it will successfully return Mesos as the course title should the unit test pass. Now that's the way it kind of works here. The way you execute on all this, you go to the Gradle tasks, right mouse click on build and say run the Gradle task. And at that point you will see the build take place, the unit test will be executed, and if all goes well, it'll say build successful. So we just simply go to the console tab here if you want to see the successful build message. You can see that the unit test did pass, so sure enough, build successful shows up. Let's go ahead and debug this application very quickly. We'll go up to the toolbar and say debug application. At this point, it's ready for the browser to come up and hit that endpoint we talked about, localhost 8080/Azure course. Once we do that, it'll trigger a breakpoint inside the Spring Eclipse IDE. So once we do that, notice we finally hit the get Azure course method. And as we navigate now through the IDE, we are looping through the results of our select statement. And sure enough, if we take a close look here, we see the JSON code return of the Mesos course. So indeed, it's working as we would expect since the unit test passed and the results are returned back to the browser. All has been successful. So now that the unit tests have passed, the compilation has taken place, and the WAR file has been created. Now the Spring Eclipse IDE will have left that WAR file in the folder you see here at the command prompt. I'm going to do dir here, and you can see that indeed we have the file right here, the WAR file. What we need to do next is take this WAR file and copy it over somewhere where we're going to build out the container, an environment where we have all the Docker tooling installed ready to go. And where that is, in my case, I have a Linux and Ubuntu Linux VM running in Azure. I'm going to go and remote into that and actually start building out this Docker container. So our next task here is to copy the WAR file from my Windows computer over into Azure running as a Linux VM. Once that WAR file is up in Linux, we'll use the Docker tooling to create a Docker image. Once run, that Docker image becomes a container. Notice here that we're going to actually upload that image into hub.docker.com for various reasons once we create that image. But first, let's start by copying over that WAR file over to my Linux VM from my Windows environment. So here you see the actual source of my WAR file generated by Spring/Eclipse. We're going to go to the command prompt and do a pscp copy command over into Azure. So to do that, we need to know where that WAR file exists. So we'll type out the source directory, users, bturkey, etc., and then copy it into the destination computer here, which will be, as you see, the mydatastore.westus.cloudapp.azure.com, and we'll name that file myapp.war file. Once we're there, we're going to log into that Linux VM and start working with the Docker tooling to create our image and then upload that image to hub.docker.com. So that completes this step. Now that we have our WAR file over on our Linux VM with all the Docker tooling, now is the time for us to actually create this Docker image. And you can see here it's a very simple equation to get our Docker image here. Ultimately, this is what we're after here. And to do so, we're going to take that WAR file we just copied over, and we're going to issue a command that glues together a Java Tomcat image that we get from hub.docker.com that's created by the community. We're going to combine those two to create our image. And there'll be a couple steps to do that. Once we do that, we're going to upload our final image back up to hub.docker.com. And as you can see over here, the actual Tomcat Java image is already there at hub.docker. We just need to layer in our application. So the question becomes, how do we combine those two elements? How do we take our WAR file that has our Java app, and how do we attach it or embed it into a Java Tomcat image? And the way we do that, as you can see here, is with a Docker file and a Docker build command. A Docker file is simply a text file, and the Docker build command is part of the tooling that comes with Docker. So you can see over here that we are ready to start working with some of these commands. Now the Docker file, you can see right here. Essentially, it's a text file, and if you notice here on line 4 is essentially here talking about that image that's already up at hub.docker.com. It's available for the world to go and leverage. And so what we're going to do, this from command says go up and grab that image, and then with that image, once we have that basically downloaded to our Linux VM, copy in our WAR file to it, and essentially into the user local Tomcat web apps directory, which is traditionally where Tomcat wants its WAR files, its web content. And then once we have that file defined, the Docker file, all we have to do at that point is issue this Docker build command you see below. And that will produce our Docker image. Now the Docker build command has a couple parameters, -t myapp. So what this means is that our image is going to be called myapp, and the period you see there at the end over here, that is essentially saying go and grab the Docker file in the current folder that we're in. So anyway, that's how you create a Docker image. Let's dive a little bit deeper in. So what you see here is the Docker build command. That is the command we talked about earlier, and once it starts executing, you can see all the steps being enumerated over here. Down here it says step 0, here we have step 1, and so on. And then when we're finished, we're going to end up with a successfully built image, and the image will have an ID, and that's what you see in this red box here, image 24011, etc. And if I go ahead and issue one more Docker command here, and you can see that below here, Docker images, we end up with listing out the images that we just built. And sure enough, you can see my app being built. There's the name my app. And then notice, of course, the matching image ID of the output of the Docker build command. So at this point, we have an image. It's living locally in our Linux VM. The next step is to push this up to hub.docker.com so that it can be easily deployed to our cluster. And of course, now our cluster can be anywhere in the world, even on premises. So at this point, what we have is our built Docker image. It's called my app. A couple more steps to do over here. One of them is going to be here, this tag command you see here. And then, of course, we're going to push it as well here. So those two commands are still needed to get this image in the appropriate format up into hub.docker.com. And what we really want that image to be listed as is Bruno Turkley /my app. Right, so Bruno Turkley represents my kind of presence on hub.docker.com, which is where I've logged in and created an account. And then my app is the name of the app that we just created. And then of course you're going to give it a tag, and that's going to be ApacheCon-1.0. That's just an arbitrary name. I did a talk at Sevilla, Spain at ApacheCon, and that's why it's named that way, but it could be named anything. A lot of people do latest for the latest, and a lot of people give version numbers. There's a bunch of discussions about how best to do that. But the bottom line is, once I tag and push this Docker image up to hub.docker.com, that means now it's available from anywhere to download. Now, naturally, I could also do a private repo, which would allow only those folks that I've allowed to do this download from hub.docker.com. But I'm going to do it publicly, meaning any of you could go out there and do this download and run my app on your in your environment. So we're going to take a little side trip now and provision our ACS cluster. Now, as we talked about earlier, you have three choices here. You have Docker Swarm, you have Kubernetes, and DCOS. It is DCOS we're going to use in this particular demo, in this session. And the way to get all this done is you have your account here, your Azure provisioned account, and we're going to go over here and go to portal.azure.com, and we're going to click New. Now, in order for this Linux VM that we're working on so far, we're going to be using that Linux VM to control the cluster, the ACS DCOS cluster. And to do that, we need to set up a kind of a trust relationship with SSH keys. So one of the first things we'll need to do before we can really provision here at the portal is go get those SSH keys on our Linux VM. Now those have been generated already. They're sitting there in the SSH folder. We're going to grab them so that when we go back to the portal, we can simply paste in the public SSH key. So the goal now is really to go to the Azure Container Service and provision our DCOS cluster. But before we can do that, we want to get our SSH key for the current Linux VM so that I can actually go in and connect up to the cluster. So this is the public SSH key, which I will need. So here I am again in the Linux VM. I'm going to grab this public SSH key. And here in the Azure Container Service provisioning process, I need to paste that in. That will allow my Linux VM to connect up to the cluster. So here we go. We're provisioning an Azure Container Service cluster. And when you do so, you can choose among the 3 different cluster orchestrators, which would be DCOS, Docker Swarm, and Kubernetes. So let's go ahead and give our cluster some information. We'll start with the username. So once we've got our username typed in there, you can see that I just pasted in the SSH public key. So let's go ahead now and finish provisioning this cluster. So we're going to go to the next screen, which is going to allow us to choose the orchestrator type. We have now added Kubernetes in addition to the 2 here, but for this particular demo, we're going to choose DCOS, which is really based on Mesos and Marathon and some other open source packages. Yeah, so we're going to click OK here at this point and provision our DCOS cluster. Go all the way over. So once we do that, we're going to go here to our resource group, which is where all our provisioned hardware lives that we've just provisioned. So we can assume now that it's done. We're going to go inside the resource group, and we're going to take a quick look at all the things that got created. And here you can see the list of infrastructure that represents our cluster. So let's go over here to deployments, because there's 2 important things that we really want to focus on here. The first thing we're going to focus on is the master nodes themselves. Those are the nodes we tell the cluster what to do, like run a container. And so you can see here we also have agent or slave nodes here, which has a different fully qualified domain name. And it's these agent nodes that the end user connects up to. So those Docker run commands are the ones that run the container. And that's, again, going to be against the master nodes. So let's keep that in mind. So moving forward here, we're going to schedule these agents to be running our containers through the master node. And again, the end users connect up to these agent nodes. So that's the way it works here. Once again, just to be clear, the master nodes is what we connect up to tell the cluster what to do. And it's the agent nodes that actually end up supporting our end users. They connect up through the load balancer to those slave or agent nodes. So to recap, we have master nodes and agent nodes, and we'll need that information later when we connect up to the cluster. So in one of the future modules, we are going to create a tunnel that is a connection from our Linux VM, our dev VM, up to the master nodes of the cluster, so we can tell the cluster what to do. And that's why we've gone to the trouble to figure out exactly what are the master endpoints and what are the agent endpoints. That way, when we connect up and run our applications, we know exactly where to go to do so. This is a crucial step where we actually build out our Docker image. So we're going to use the docker build command -t myapp, which will be the name of the image, and then dot means the current directory. Notice in the lower right, we've got the Docker file I showed you earlier. That's going to be the blueprint by which this image is built. And it looks like it was just successfully built and marched through and copied our WAR file in the appropriate Tomcat folder. And so at this point, we can issue the Docker images command and validate that our image is there. And indeed, there is our image ID. Now, before we can push this up to hub.docker.com, we need to tag it. And the tag command here takes the image ID and gives it a name that will be present on hub.docker.com. Bruno Turkley /myapp /apacheCon. And we'll go ahead and list it after doing that with the Docker images command. And sure enough, the tag command worked. You can see there it's been tagged correctly. At this point, we're ready to do a Docker push. That Docker push command will take this image and push it up to the Docker repository. The good news here is the hub.docker.com repository will track all the images previously uploaded, so this could save significant time on big uploads. So at this point, the whole entire image has been uploaded. Let's now go to hub.docker.com and take a look and make sure that that correct image made it up there. So again, hub.docker.com, we'll log in under my ID. We'll scroll down, we're looking for my app, /ApacheCon-1.0. We scroll down here, there's my app, and from here we're going to go ahead and click on the tags element here, and sure enough, there it is. So everything worked correctly here, the tag, then the push. So the remaining work here is to actually get our image downloaded from hub.docker.com and running on our cluster. Now essentially the bottom line here is that we are getting ready to tell the masternodes of our DCOS cluster to run our container. And the way we do that is we're going to tunnel in, we'll talk more about this in a moment, but we're going to tunnel into these master nodes and tell those master nodes, can you go ahead and schedule the running of our uploaded Docker image to the agent components of our cluster. So here on the left are the master nodes, and then as part of the deployment you're going to have one or more agent nodes, and the agent nodes is really what the end users connect up to, but us as the cluster administrators, we talk to the master nodes. So that's what we're going to do next. So there's a lot going on this particular screen. Let's talk through it a little bit. As we discussed, we have our DCOS cluster here running in Azure, and there are both agent nodes and master nodes here you can see that I'm highlighting. Now that's how this is all going to play out. We're going to basically be setting up a tunnel over here, as you notice, to the master nodes. Now that tunnel essentially allows us to communicate from our Linux VM over to this cluster. So our Linux dev machine is going to set up a tunnel over to these master nodes over here. And once we do that, we can start telling those master nodes what to do. And the way we're going to do that is through a curl command. Now curl is simply an easy way to issue HTTP communication to some endpoint. And you can see examples of both of those things happening here. What we're going to do here in step one is establish that tunnel. And if you look down over here, you'll notice, for example, that indeed we have the sudo command over here. And we're going to lay out the different parts of that command to make a tunnel. Now that tunnel relies on those SSH keys that we established earlier in the previous step. That's why we did that step, to kind of validate that we need SSH keys. And now the way that works is I'm going to establish a tunnel, and I'm going to use localhost over here. If you notice, we have a localhost piece into this command, and that simply means that if I issue a command in curl and I talk to localhost, what that really means is that I'm talking over here to the master nodes. That's how the tunnel works. Even though I'm going to talk to localhost, which would typically mean the machine that I'm on, in this case, by setting up a tunnel, it means that anything that talks to localhost really talks to what I'm pointing to, which is the master nodes of our DCOS cluster. Now you need to go up to the portal to actually retrieve those nodes, right? We're going to see that. We're going to need to grab the address, the domain DNS name for our master nodes, which you can see is Bruno MGMT for management nodes, .eastus, etc. Now the agent nodes have a different domain name, and that's what our end users will connect up to. Okay, so that's about creating the tunnel, is issuing this SSH command, which ultimately connects up to, as you can see here, port 2200, and that's the port that DCOS is listening on in the master nodes, and that's the port we connect to. Now the next kind of piece to think about here is the curl command. This curl command is ever so important because it is this curl command that tells the DCOS cluster to run our application, to run our image as a container. Now notice a few things here. We're doing a post. we're talking a local host, and as explained, this really means go to the master node. And the core piece of information here is this marathon.json file that you see right here. This marathon.json file defines the way we wish to run our container, and that we'll explore in just a moment. But the key point here is that in order for us to have our image run as a container in our cluster, and that image is living currently on hub.docker.com, the way to get all this done is you set up a tunnel, and then you issue the curl command to basically tell our cluster, go ahead and download that image and run it as a container. So let's dive in a little deeper about what this marathon.json file is all about. So what we're looking at here is the marathon.json file, and there's some simple things to notice here. For example, number one is that the ID of the app we're going to run in the cluster is simply going to be my app. Now, other kind of noticeable things here is the fact that it's going to be a Docker container, which is what we created, and this is the actual image living up on hub.docker.com. So it's exactly at this line that we know that the cluster ought to be running the image as a container from that particular location, which we uploaded from before. Notice it says 2.0 there on that line. That's because I did another deployment to 2.0, but for all practical purposes, it could be any version that's tagged up there at hub.docker.com. A few other things over here that you'll see. We'll talk more about this in a moment. But the point here, of course, is the fact that marathon.json is the blueprint that defines how we will run our image as a container in our DCOS cluster. So let's actually do a demo of this stuff in action. Number one, creating the tunnel, and number two, actually issuing the command, the curl command, to run our image as a container in our DCOS cluster in Azure. So as explained, now it's time to actually set up the tunnel that we described earlier to our master nodes of our DCOS cluster. Again, creating a tunnel so that we can tell the cluster what to do. Again, explained earlier is that localhost really points to the master node of our DCOS cluster. We got that name from the portal when we created the cluster. Maybe we'll take a side trip and take a look at that real quick. Now that we've got that tunnel established, we can actually look at the SSH process that's running in the background, routing traffic to that master nodes. So that's how that happens. Now at this point, let's dive a little bit deeper into the marathon.json file, which contains the metadata of how we wish to run our container. Looking at some line numbers over here, you'll see a few things. The ID of our container, and that's really, once we go and look at the portal, we'll see that ID. What kind of hardware we want. We want 1 CPU, 512 of memory, etc. And that kind of limits the way we throttle our app. Now there are different types. This is a Docker. There's the Apache Con-1.0 VM. This is the ports that are going to be mapped to our running instance. And of course, we also have the Java runtime requirements that are kind of indicating how much memory to give that particular Java instance. And so that basically is most of what we're talking about. There's some health checks that are done by DCOS, and that's how that metadata indicates how we want that done. So that basically defines the marathon.json file. I wanted to take a kind of side trip about how we actually go and find out the master node DNS. And the way we do that is we start with our resource group, which is essentially the container for our cluster. There is mine, the Bruno-Mesos2. And as we go over here, we'll notice it says 2 deployments here over in this window here. Now that is also created upon the actual creation of the cluster itself. So you can see my 2 deployments. Let's go to the first one for ACS. And as we see over here, it gives us a bunch of important information. And here you can see the fully qualified domain name of our master nodes in the cluster. And of course, this is the fully qualified domain name of the agent nodes. So it's in basically these nodes over here that we tell the cluster with curl commands what to do, and our end users are going to connect up to the agent nodes and connect up to our running application, our Java app. So that's kind of the relationship between the master nodes and the agent nodes and where you get that information. So now that we've got our tunnel set up, let's take a little bit of a closer look on actually issuing the curl command to run our application. So again, explained earlier is that local host really points to our masternodes by virtue of the fact we set up that tunnel. And again, we're passing in the marathon.json file, which contains the metadata about how we want our image to run as a container. So you can see here the metadata is being returned after the curl command, which is the DCOS way of telling us it ran. And let's take a quick look, and indeed it's echoing back at the output that reflects what we told it to do. So this is returned back by DCOS. It contains the metadata that really describes how it was physically run. This is really confirming the metadata that was used to tell DCOS what to do. And in this case, you can see it ran according to our directions, and it's basically a way to validate for us that it's running. Now we're going to set up a tunnel from a machine that has a browser, which is back at my Windows machine, and I use PuTTY over here to essentially tunnel in from my Windows machine this time so that I can issue the browser, because we want to basically go look at the DCOS cluster with a browser now, and my Linux VM did not have one. So I'm setting up a tunnel now using PuTTY from my Windows machine up into the master nodes so we can view visually through a browser our jobs running inside the cluster. And this is the part where we want to basically verify that the application is running as I would expect. There's two endpoints, Marathon and Mesos. Let's go ahead to Marathon, and indeed you can see my app is running in the cluster. Again, what we're doing is we're using the browser to kind of visually look at what's happening in my cluster. There's a bunch of commands here. We can start our apps, kill our apps, scale our apps, etc. And actually see what's happening. And again, it's through this web interface provided by the master node of our DCOS cluster. And we can also go to the other endpoint here and see what kind of short-lived jobs might be running here. And this is another view called the Mesos view. It allows us to see what tasks might be running. So there's Marathon and there's Mesos, two ways to actually look at the way our cluster is behaving. You can see the resources that are consumed and so on here. And again, this is for cluster administrators to get an inside peek at their cluster. And we set up a tunnel basically from any browser machine that is running. Okay, just to add a little bit of context here for why we created that tunnel from Windows into the master node of our DCOS cluster, it's a very simple reason, is because the Windows Dev PC does have a browser built in and it has a GUI. Now with that said, we could have gone to the Linux Dev VM and created a GUI for that and then therefore install Chrome or some other browser, but we decided that it might just be easier to go ahead and create that tunnel from Windows and then just use the browser there. So that was the thinking. And this site over here, Bluehost, my.bluehost.com, is perhaps a good place for you to go and learn some of the steps here to do that. Essentially all you're doing, as you can see here, is you're going to need to generate a PPK file and then configure PuTTY. PuTTY is a connectivity tool that you can pretty much download for free at putty.com, I believe, and therefore be able to do everything you see here or just saw in that previous demo. So just to be clear, it's actually putty.org, as you can see here. That's the place to go to get PuTTY and basically do those steps I just kind of discussed, to both do an SSH session with direct connectivity to a VM or to actually just create a simple tunnel. So all that is here, easy to use, easy to download, and free. So this is where the rubber meets the road. We're actually going to go now navigate to the agent nodes, which we talked about earlier. That's where the actual container is available to our end users. And as you know, this particular URL did a default search for ESOS, and that's why you see Mesos show up. So it worked correctly, but let's pass in another parameter here. So we'll say question mark, title equals Docker, and sure enough, those courses are showing up. And so it's working as we would expect here. The URLs are working. If we go back to the database, you'll see indeed that, for course title, there are records on Docker containers, so it did work correctly. And really, this represents the end game for this particular demo. So I believe this graphic gives you a pretty good depiction of what's happening here. The user commits code, the developer that is, commits code into GitHub or what have you, anywhere pretty much, and a build process automatically takes place. That typically means that a download of the source code and some of the Devops pipeline tooling gets downloaded to a Jenkins build server where a number of things happen, everything from compiling to testing the application. If those things pass the various stages of tests, both unit tests, integration tests, and a variety of other tests that you might want to implement, you might want to get that containerized application into staging and ultimately deploy it there, at which point you could decide, perhaps with human intervention, that it should go to production. And so at that point, that you can kind of see the big picture of what a pipeline looks like. And there's feedback here, so as each of the different stages goes through and things in production happen, users end up using that deployed application, they have feedback, and this virtuous cycle continues to repeat, and that's really where the business value comes from. We talked about that early in this course or in this presentation, and you can see now that effectively continuous integration, continuous delivery is really the way modern companies are moving forward. So what you're looking at here are 9 steps that comprise the pipeline, the DevOps pipeline. Now, the way this typically works is it's 100% automated. And so you can see the DevOps guy there, whether that's a developer or a QA engineer, someone is responsible for the pipeline in terms of it running successfully. And so the idea here is that all these steps are automated. Now, I've developed some of these steps using Python as an example. We'll look at that next. So let's take a quicker look at what's going on over here. So imagine in step 1 that the developer is on the Windows machine, and in our case, they're writing this application using Eclipse or Spring, what have you. And as they compile, Gradle has built-in unit tests that's happening at the developer workstation. The next thing that's going to happen is code gets checked into GitHub when the developer feels he's ready to release his code. At that point, a webhook gets triggered, and what a webhook is simply a signal that GitHub can send to my Jenkins build server. And what that really means is that Jenkins knows that someone just checked in code, so what it will do is do a git pull or a git clone, take that developer source code and bring it upon into the Jenkins build server. What Jenkins will also do is download the Python tooling that I have written in my example, which contains all the kind of capabilities to execute the rest of the pipeline. This means that the Jenkins build server is a blank generic VM, and all it needs to do is kick off the pipeline, and everything kind of happens in an automatic fashion. And so you'll notice here in step 4 that Jenkins will now download the developer code and the DevOps script code and run it through Gradle, once again running the unit or integration tests on that Jenkins build server. So now that's the second time that we did a build and a unit test since the developer checked in their code. And at that point, perhaps we ought to now automatically build a container using the compiled WAR file as we've seen earlier in this session. And so step 5 is about building out that Docker container. And then once we've done that on the Jenkins server, we're ready to do some more testing. What we do at that point is we run that container on the Jenkins build server. Now remember, the beauty of containers is that it has all its dependencies. And so once it's running locally on the Jenkins build server, we can run additional set of tests. In this case, I'm running some integration tests in Python, and you see that in step 6. I'm running a third set of tests against the running container itself. So imagine that in step 6 that succeeds. Well, that's a very good indication that this container now can pretty much run anywhere. But we're not done testing. That brings us to step 7. Let's go ahead now and take that container, and that image rather, and deploy it up into the hub.docker.com so that it's available for other departments, maybe other QA departments. Maybe we'll just automatically push this in step 8 and 9 into staging. So that brings us to step 8. Now that that image is sitting there at hub.docker.com, we are ready now to actually set up a tunnel between the Jenkins build server and the master node of our DCOS cluster. And by setting up that tunnel, we can now run the very same commands we did earlier to actually deploy that running image as a container in our DCOS cluster. Now, for argument's sake, we're going to say that's the staging area. Perhaps you have a production cluster as well. And so finally, in step 9, we do additional integration tests against that running container in Azure in the ACS in the DCOS cluster. So that's by that point, by the time you get to step 9, you've done 4 levels of testing. And at that point, perhaps it's appropriate for someone in the QA department or someone in charge of DevOps to say, hey, let's flip that switch and put that running container in production. So that's the DevOps pipeline. In the next demo, let's actually see this in action in Jenkins. Now, real quickly, let's take a look at what's happening. So in the Azure Data Center, we've provisioned a Jenkins VM. And let's say that within Jenkins, we define this new pipeline, and we call it HTTP service. You can call it whatever you want. Now, also in GitHub, notice that the developers checked in their code, and we've already, as DevOps engineers, written a bunch of Python code that's also sitting up there in GitHub. So when the build process gets kicked off in the pipeline, the first thing that we're going to do is download the code from GitHub onto our Jenkins build server, in addition to the code that we're going to run and test. So in a sense, this is part of the automation, that the pipeline is somewhat empty before the build process kicks off or the pipeline kicks off. And at that point, we're going to go download the assets we need to execute that pipeline. Now on this screen, you can see that I have 2 pipelines, one called Atmosphere, one called the HTTP service. Those have been pretty much set up, and you'll notice in the upper left corner the new item menu selection. That's how you create a new pipeline, and then you run a bunch of script code for it. And what you see here is that pipeline itself. We're in the HTTP service pipeline in Jenkins, and it's in this area where we'll start really defining how that pipeline executes. Let's now turn our attention into a real active pipeline that we're going to execute and actually follow through from beginning to end back to those 9 steps we discussed. So as you recall, in this pipeline series of steps, there is a Python module that accomplishes each of these different components. And so what we're going to see next is a series of these Python scripts executing that really deliver all these steps for us. Now here we have a couple pipelines defined. Let's go into HTTP service and really go into the configuration so you can see how it's set up. Now beyond just giving the pipeline a name, we're going to go down to this kind of window, the pipeline window, where we have all these Python scripts. So this is the Python code that runs the pipeline. The first thing we do is clean up the DevOps pipeline. And here you can see the DevOps scripts themselves that then follow here. In other words, we download all the Python scripts we see executing over here. So in addition, these Python scripts are going to be downloading the code, they're going to be compiling the code, and so on. So if we go over to my GitHub repo, you can actually see the DevOps, the Python code that I wrote. So let's take a look at it. So these are all the scripts that execute the pipeline. So whenever we actually run this pipeline, all these scripts get downloaded to the Jenkins build server and execute. One of the things I did is I've actually tracked the state of execution through an external MySQL database. So let's go ahead now and just run that pipeline and watch it actually execute. So we'll click Build Now here, and what you'll notice is that a little build number 87 is executing, and we can kind of drill down on the console output to see it executing. So all those 9 steps that I outlined now are represented here by the Python scripts that are currently executing now that they've been downloaded here at the beginning of this pipeline execution. So you can pause this, kind of read in more detail here what I have to say, but essentially all those 9 steps are being executed through Python script. And notice at the end of it all too, at the end of each of the steps, I'm displaying the contents of my MySQL database table, which really tracks if there were any errors that occurred here. So you can see here that in each of the different steps that executed, we're actually recording whether it was successful or not. And if it was successful, no errors were discovered here. You're looking at another view of the actual pipeline. You can see here that at each of the steps I'm kind of documenting here as I go, so that ultimately I can see exactly how the steps are executing and if there are any mistakes. So at this point, we've gotten to the end. We're at the point now of running this in production. Everything is successful. Now, if you're interested in more information about all the gory details of how I basically built out that pipeline, I've got a 12-part series here defined on my blog here, and you can see here all 12 steps are kind of really drilled into in detail, you know, for everything, the high level description, some of the tooling and so on. Go all the way here, say in the middle of one of these guys, you'll see that I also present the actual source code itself that represents the pipeline execution in Python. So all the Python code here, for example, you see the docker run command being executed from within Python. So this gives you a little bit more detail on that really quick overview of DevOps, but I at least wanted you to see some of that execute so you know how some of the pieces fit together. This takes us to the final slide of the entire session, my conclusion. I want to thank you for listening in. You can reach me at bturkley@microsoft.com. Hopefully you learned a lot about the entire process, how DevOps fits in, what containers mean, what orchestrators mean, how to deploy and build out an application that ultimately gets run at scale within the Azure Container Service. Now, clearly, in my opinion, this is the future of compute. This is what we're going to see over the next couple of years really explode in popularity. So I hope I gave you an accurate glimpse of things to come in this space. I feel pretty confident about kind of the way I delivered it, that it's going to give you the value in terms of the overview and how things all fit together. So thanks very much and have a great day.